Yes,
So
okay.
it is a great pleasure for me to introduce our first speaker for today, Professor Makoto Sakuma from Hiroshima. So please.
Thank you very much for your introduction. So before starting my talk, I'd like to express my deep thanks to the organizers for their kind invitation. And it is my great pleasure and honor to give a workshop, to give a talk at this workshop. So anyway, so I have moved to Osaka Metropolitan University because I have retired from Hiroshima University 2.5 years ago. Okay, so and this is a joint work with Shunsuke Sakai. Okay, and here is a plan of my talk. First of all, I'd like to propose a problem motivated by Ian Agol's talk given in Budapest in 2001 that is concerning two parabolic generator Kleinian groups, namely Kleinian groups of this type. So it has one complex parameter. And then I will talk about the related results. And secondly, I will give a rough statement of the main result of this talk. And then I will talk about non-positively curved cubings and right-angled cubed polyhedral decomposition. And I was very much excited by Andrei Bestny's talk yesterday because his talk is in some sense related to this topic. And finally, I will talk about my main result and key ideas and examples. Okay. So let L be a prime alternating knot or link in the C-sphere. And by the symbol L, I denote the reduced prime alternating diagram. So if we are given a diagram, we have two checkerboard surfaces, black surface and white surface. And let X be the link complement, and let E be the link exterior. Okay, and then by the theorem which Andrei explained yesterday, and also by using the result of Menasco about alternating links, we know the following theorem. If an alternating prime link L is not a 2n torus knot or link, then L is hyperbolic. Namely, the complement of X admits a complete hyperbolic structure of finite volume. So X is identified with the quotient of the hyperbolic street space by the action of discrete isometric groups, gamma. And of course, this gamma is isomorphic to the fundamental group of X. In other words, the link group of L. Okay, and and in his talk in 2001, he announced the following theorem. And the proof following his idea was written down by Adams. And the generalization of the theorem was given by these people. Okay, the theorem says that the surfaces SB and SW are quasi-Hookean. This means the following. First of all, okay, consider the open surface, interior of the surface. Then, of course, it's embedded in X. Then the first statement is that the fundamental group injects into the knot group, link group. So let gamma B, then so this group, gamma B, is identified with the subgroup of PS2C. And the statement says, the theorem says that this group is quasi-Hookean. This is equivalent to the condition that the limit set of this group is a circle. And I will show you some picture. Okay, so by Thurston's trichotomy of essential surfaces in three manifold, for this group, we have one of the following folds. For quasi-Hookean, in this case, the limit set is a topological circle. Okay, and the second case is the group has an accidental parabolic. So in this case, the limit set is a continuous image of the real line, but many points are identified together. And the last case is a semi-fiber. In this case, the limit set covers the whole Riemann sphere. And Agol has shown by using non-positively covered cubing that this does not happen. Only this happens for these surfaces. Okay. Then we have the following setting. So let P be the universal covering. And we have a black surface and consider its inverse image. Okay. Then it is and look at the component of this subspace. Subspace. Then the injectivity of this group says that this component, each of the component is identified with the universal covering of this black surface. So it is identified as a hyperbolic plane, but it is embedded in the three-sphere in H3 in a very complicated way. Okay, and now look at the boundary. Look at the boundary, ideal boundary of the hyperbolic space. Then we have the boundary of these planes, which are topological circles. So we have infinitely many topological circles on the ideal boundary, and for each plane, of course, the stabilizer of each component is conjugate to this fundamental group. Okay. So I'd like to consider the following problem. Describes the intersection pattern of these circles. So you have black circles and white circles. And what is the intersection pattern of these circles? And the main purpose of this talk is to give an interpretation and a refinement of Agol's answer to this problem. Okay. And let me explain Agol's answer to problem A that was given in Budapest. Okay, pick a base point to B plus in the above the projection plane. Okay, so the link group gamma is identified with the fundamental group of X with this base point. And for each black region, say, choose a monotone path from B plus to the center of this phase. Okay? And let gamma bi be the fundamental group of the union of this arc and this surface with this base point. Then, of course, this is a subgroup of gamma. And similarly, we have a subgroup gamma wj for each white region. So we have finitely many subgroups of gamma. Okay. And before describing Agol's claim, I'd like to talk about the key fact behind his claim. Okay, this is the key fact. There is a non-positively curved cubing of the link exterior such that these black surface and white surfaces are totally geodesic. And secondly, these arcs are geodesic and perpendicular to this plane. This factor plays a key role. Okay. And then let me explain Agol's claim. In his slide, he claims the following. The intersection pattern of the
excuse me,
yes,
may you return that fact? So it's so crucial. So
here, this part?
Yeah, sure.
And is it okay? So I define the group gamma. So for each black region, we consider this path and consider the fundamental group of this surface with this base point. So all of the groups gamma bi are conjugate to each other. Okay, and also we have white surfaces, and Agol looks at the limit set of these subgroups. Okay, and may I go further? Okay. The intersection pattern of these limit circles is illustrated by the following diagram. Let me explain. So consider a link diagram and look at only black regions. And for each black region, consider this slightly bigger circle, but that passes through all crossing points. So in this case, we have three slightly bigger circles which are tangent at these crossing points. Okay. And similarly, white surface, white regions consider these disks. So for W0, the circle is something like this. Okay, and takes a union. Then we obtain black circles and white circles. Okay, but in this case, green, blue, and green. And Agol claims that the intersection pattern is illustrated by this picture. Okay. And the main purpose of this talk is to state our interpretation of the statement. And but before that, I'd like to explain why Agol claims introduced this claim. This claim was used to prove the following theorem. Okay, let L be a hyperbolic two-bridge link. So we have two bridges and braid and two bridge. This is two bridge, not one link. And let M1 and M2 be non-elementary pair of meridians in the link group. So by a meridian, I mean the element of the link group, which is represented by a meridian circle with together with a path from the base point. And by non-elementary, I mean M1 is not equal to M2 or M2 inverse. Okay. Then he claims the following. One of the following holds. First, this meridian pair is equivalent to the upper or lower generating pair. So this is upper meridian pair, and this is a lower meridian pair. And in this case, M1 and M2 generate the whole group. And but let me explain what we mean by equivalent. Two meridian pairs are regarded to be equivalent if they are related in this way. Namely, you may replace one of them with its inverse, or you may take the simultaneous conjugacy. This is the equivalence of meridian pairs. And okay. So, he claims that non-elementary meridian pair is either equivalent to this standard upper-lower meridian pair, or the group they generate is a rank 2 free group, which is geometrically finite. Okay. Let me point out that the meridian pairs up to equivalence is there's a bijective correspondence between this set and the set of all proper arcs embedded in the link exterior modulo proper homotopy. So you can present the meridian pair by an arc joining the meridians. Okay, this is his theorem, and he used this claim to prove this theorem. And I'd like to explain how to use this claim in order to prove this theorem. This is as follows. I will show by an example. Consider a meridian pair illustrated by this arc. Okay. Then we can, and this is a picture corresponding to this one. So this is a picture of the ideal boundary. Okay. And M1 is here. Then we look at this overcrossing. Then and corresponding points. This corresponds to the parabolic fixed point of M1. Okay. And similarly for M2, we move this to this overcrossing and look at the meridian here. And this point is a parabolic fixed point of M2. And the action of M1 and M2 is described as follows. This maps this limit circle to this circle. To be more precise, it maps the outside of this circle to the inside of this disk. And similarly for M2. Then he says that we can appeal to Klein-Maskit combination theorem to show that the group they generate is a geometrically finite rank 2 free group. And we wanted to really understand his argument, but we don't know how to apply Klein-Maskit theorem, but we can prove this theorem. as follows. We can show that by using this technology, that the group they generate is free. And moreover, it has the non-end domain of discontinuity. So then, by appealing to the theorem by Musket and Swallow, which says that if a two parabolic generator has non-empty domain of discontinuity, then it is geometrically finite. So we obtain this theorem, even though we can literally follow his argument, but anyway, we can understand this theorem. Okay, and I have one comment about this theorem. By using more general theorem, namely Canary's covering theorem and the relatively recent result by Milchap-Borden concerning commensurability of two-digit complements, we can replace in this theorem the two-digit complement with cusped hyperbolic manifold of finite volume, and the pair of meridian with pair of parabolic elements. So we obtain the following generalization of this theorem. So let X be a cusped hyperbolic three manifold of finite volume, and let mu1, mu2 be non-elementary pair of parabolic elements. Here, non-elementary means that they are not commutative. Then one of the following holds. The space X is equal to the two-digit complement, and mu1, mu2 is equivalent to the upper or lower meridian pair. Or this group is a rank 2 free group, which is geometrically finite. So this theorem uses more modern technology, but this proof is very, very nice. It is very intuitive. So I like this proof. And but this has some small application. As a corollary, we have the following. Let L be a hyperbolic link with Brit index greater than or equal to 3, and pick two meridians. Then the subgroup they generate is a rank 2 free group. This is the corollary of that theorem, and this gives a partial answer.
Excuse me, is it the corollary from the theorem or from the generalization?
From this theorem.
And can I see the generalization?
Oh, sorry.
Yeah.
Sorry. I'm
Yeah.
sorry. The letters are too small. So
Yeah.
So shall I repeat this theorem? So this, okay, suppose let L be a hyperbolic link with the index greater than or equal to 3, okay? Then of course the link complement is a cusped hyperbolic manifold of finite volume. And pick two meridians. Of course it is two parabolic elements. And since our link is not a two-bridge link, this does not hold. So this means that the group the meridians generate is a rank 2 free group, that is, which is geometrically finite. This is a proof of this corollary by using this generalization of Agol's theorem. Okay, and this is in some sense interesting because it gives a partial answer to a conjecture proposed by Boron. He conjectures the following. So let L be a link with bridge index B, and pick n. Let n be a number small less than b, and pick n meridians in some sense independently. Okay, then the group they generate. Oh, sorry. Is a is a free group for some k is less than at most n. So, so this corollary gives us partial answer. Answers this. Apparently solves this conjecture when n equal 2. So anyways, the claim was used to prove this theorem. This is the first remark. But I have another. Is it okay? And another remark is the following. Actually, the main purpose of Agol's talk in Budapest was the following. This is a part of this more big theorem. Agol gave us a complete classification of non-free two parabolic generator triangles. This is the first result. Actually, he has shown that if a group, before that it was proved by Adams that if a triangle group is torsion free and non-free, it is a two-bridge link group. And Agol generalized this Adams theorem into this form. So if a two-parabolic generator triangle group is non-free, then it is either a two-bridge link group or so-called heckoid group. That is a generalization of Hecke group. And this picture nicely illustrates this result. So the region, this third region, or maybe outside of this I, any parameter omega, for any parameter omega, this group is free, rank 2 free group. And in the I, you have a lot of dots. And these endpoints correspond to two-bridge link groups. And the intermediate dots are so-called heckoid groups. And moreover, anyway, so this picture was produced by Yasushi Yamashita, and that is based on the theory of Kin series and my joint work with Akiyoshi, Wada, and Yamashita. Okay, so and this, yeah, okay, and moreover, he proved the following: for each such Kleinian group, he classified parabolic generating pairs of such groups. So namely, he has shown that this theorem shows that each two-bridge link group has precisely two parabolic generating pairs, upper and lower. And for heckoid groups, it has a unique generating pair. That is Agol's theorem. And when I heard about his theorems, I was very much interested in his work, because at that time I was working with people on the same related problem. Okay, so I immediately asked young Agol to send me his slide, and I repeatedly asked questions to him. Then finally, he encouraged me to write down the proof. And very fortunately, just before my retirement, I could manage to give a full proofs, and it's already published. So this part is proved by in a joint work by Akiyoshi, Oshika, Parker, and Yoshida. And for this part, we give an alternative proof by using knot theory technique. And this is a joint work by Aimi D. Sakai. And but we are not satisfied with this proof because we did not understand this part. So this talk is motivated by our desire to obtain a rigorous understanding of Agol's original argument, in particular this part. Okay, so this is the main purpose of this talk. Is there any question so far? Okay, so let me explain our interpretation of this claim. So let L be a prime reduced alternating diagram. And okay, now let's look at the black region and the white region. Okay. Then the following holds. If the black region and the white region are adjacent, meaning they share an edge, then every picture shows this pattern. And we can actually show, then we can see that the limit set of gamma EI and the limit set of gamma WJ intersect transversely in precisely 2 points at 2 parabolic points, which correspond to these meridians. And otherwise, the limit set disjoint. Okay, well, this part is not so difficult. The second part is difficult. We look at the two regions of the same color. For example, we look at two white regions, and if the two white regions do not share a vertex, then they are disjoint. This part is also easy, but if they share a vertex, then this picture is not literally correct, because okay, Agol's picture illustrates that this circle intersects infinitely many points, but this is not correct in general. In general, the intersection of limit set is very complicated. It is control set in general. And there is some symbolic representation of this intersection. So I will explain this later. This is our main theorem. Okay, and so this is a key part. And but before that, I'd like to explain how this intersection arises. Okay, first of all, the black for this intersection.
May I see the statement?
Yes.
May I see the statement for white or black?
Yes. White
So,
and black.
so the last statement, yeah. No,
Yes.
no, the last statement too.
That's white and white.
Okay, they share a vertex, and then
Okay, then the limit circles intersect. Of course, they intersect at these parabolic fixed points, but they also intersect at infinitely many points in general, and it's a control set in general. This is, and this part I don't explain. I can't explain just now. Later, I will explain what this means. Is it okay?
okay.
Okay, so, but before that, I'd like to explain how this intersection arises. Okay, the first one is black and white. In this case, the fundamental group of black surface and the white surface do not intersect. However, we have the following phenomena. If there is some point which belongs to both limit set, and the stabilizer of this point in gamma bi and also gamma wj is an infinite cyclic group generated by a parabolic transformation. So this is a infinite cyclic group generated by a parabolic transformation, but they are transversal and they generate z plus z. So even though they don't intersect, but in this way, the intersection appears. This is the first phenomenon. And for same color case, it is known by the work of these people, which also contain this phenomenon. It says that the intersection of these two limit sets is equal to the limit set of the intersection of the subgroups. And moreover, this group is geometrically finite, and hence it must be a finitely generated free group. And we think there is an algorithm for understanding for constructing a finitely generating set for this group. And let me explain this by an example. Okay. Now let's look at this white. Okay, so let's look at the white. No, this is figure knot. And look at white regions, and look at the two white regions which share these vertices crossings, and let gamma W0 be the fundamental of this arc plus this white surface. And we choose its generator alpha beta as follows. Look at the spine of this guy and take a maximal tree, and alpha is this one. So we start from V plus and go to W0 and go on alpha and come back. This is alpha, and similarly for beta, and we have this generating system. Then we can show that the intersection of gamma W0 and gamma W4 is a rank 3 free group generated by these elements, where lambda 1 and lambda 2 are actually longitude, and so they are conjugate. But this is a very strange element. So this is our main theorem. And the key tool is non-positively curved cubings for white surface, black surface, and the link exterior. So next, so I'd like to talk about non-positively curved cubings. And so I'd like to begin with canonical non-positively curved cubings of white surface, a black surface. Okay? So please note that the black surface contains crossing arcs, and these are parallel copies of crossing arcs. And if you cut this surface by crossing arcs, then you have disjoint union of disks. And now consider its spine. Okay? And we also cut this disk by these spines. Then the remainder is can be regarded as a copy of two squares. Okay. For example, look at this guy. Okay, you have a spine, and so you have spine, and crossing arcs. So crossing arcs, and black edge. And here is the central point. And I divide this into two squares. So each of these pieces can be regarded as a union of two squares. And so this gives the decomposition of the black surface into squares. And this decomposition is non-positive curved because if you look at each vertex, for example, if you look at this vertex, then you have 6 squares. This means that the angle is 3 pi, that is bigger than 2 pi. And for this case, we have 2 pi. But anyway, so we don't have pi. So we don't have a vertex whose angle is less than 2 pi. So this is non-positively curved. Yes. Okay. This is a checkerboard decomposition. And this decomposition should be regarded as a decomposition of compact surface, okay, in the living in the link exterior. And by replacing this cube, so this is a not boundary with this infinite guy, then you obtain a cubing of this open surface. And again, we obtain non-positively curved cubed complex. Again, we obtain non-positively curved complete metric space, SP. Okay. Now, let's look at its universal covering. Then we can regard the universal, but before that, okay, let me explain this key part. So, of course, our open surface is obtained from this compact surface by adding half infinite annulus. But we regard this as follows. It is obtained from the spine by adding this half infinite annulus. Okay. Then this decomposition leads to the decomposition to the universal covering. So the universal covering of the black surface is obtained from the universal covering of the spine. So this is a tree by adding Euclidean line across a half interval. So this is spine, and by adding this, we add this space in this way. So this is the picture of the universal covering. And similarly for W2, okay? And now we are interested in the geodesic rays in this space. Okay, let W0 be a fixed white region. and let MW0 be the center of the face, and take the universal a lift to the universal covering. Okay, and so we consider this point, and consider we'd like to describe the geodesic rays in this spine. Then this way, then of course it is represented by this infinity sequence, namely white region crossing white region and so on in this way. So white region crossing white region and so on. Of course, this crossing CI is a common crossing between WI and WI plus. And since it does go back, so CI and CI plus one are different, and they are also different. And and we can also express the geodesic, encode the geodesic ray in the universal covering of the surface as follows. So in this case, the geodesic ray can enter into this Euclidean space. So such a geodesic ray is represented by this symbol. So white region crossing white region, and finally some vector B in this space. And if this vector B belongs to the boundary, then this has another expression, because if B lies on the boundary, then this is in the spine. So in this case, you have this geodesic ray can be represented by this infinite sequence. Okay, this is a cubical decomposition of white surfaces. And there is a natural cubical decomposition which includes that cubical decomposition of black and white surfaces of the non-link exterior. Okay, so this was first found, according to Rubinstein, this kind of decomposition was first found by Aitchison and also Agol. And it was rediscovered by Dylan and Yokota and others. And I don't have time to explain carefully this decomposition, but it is a non-positively curved cubing of link exterior or not to complement, such that the black surfaces and white surfaces are union of mid squares. So here is a P. Okay, actually, every cube in this space is isotopic to this picture. Namely, if you have a crossing, then we have a crossing arc, and we have a pair of cubes. And by collecting these cubes, we obtain a cubical decomposition. And please note that white surface and black surface is mid cubes. So they are totally geodesic and they intersect orthogonally. And sorry, I don't have enough time to explain. But now we look at the universal covering, A cubed. Then, okay. And, okay. And now, because that we have, okay, in the link complement, we have two base points, V plus in the above and V minus in the above. And these are vertices of a cubical decomposition. And we cut the link complement by the union of black surface and white surface, and consider its inverse image in the inverse covering. So, namely, okay, we consider, for example, this compact cubing and its universal covering, and cut this space by the inverse image of black and white surfaces. And then it has two kinds of components. One component, one of them, so those one which contains the lift of V plus, and the other contains the lift of V minus. But they are essentially equal. Just now look at this guy. Then it is a union. So if you look at each cube, then each cube is divided into these small pieces. and we collect the pieces containing V plus. So it is right angled. So, and you obtain this kind of picture. And the key point is it is observed by Thurston and Menasco and others that the combinatorial structure of this guy is essentially equal to the link diagram in this way. So anyway, I'm sorry for last case, I have 10 minutes. So I think I can skip here. And okay, let's look at the universal covering of A. This is good definition. So this is a complete cat-zero space. And the ideal boundary of the complete cat-zero space is defined to be the space of the rays modulo asymptotic. So if this, okay, so this is a space of asymptotic classes of geodesic rays. And it has a natural topology, so-called cone topology. Then it is proved that this space is identified with 3 ball and its boundary, and sigma is the inverse image of the black surface or white surface. This is identified with disks. Okay, and we explain, we deformulate this theorem in the world of this space. But since this is essentially equal, I'd like to skip this part and I'd like to explain one key proposition. I'm very sorry for my rough explanation. Okay, please recall this symbolic representation of geodesic rays. Okay. Now consider link diagram and consider 2 distinct regions. And let sigma W0 be some particular component of the inverse image of the white surface. So this is a total geodesic plane. And look at its center and consider a geodesic ray starting from its center and represented by this sequence, by this symbol. And choose another geodesic ray issuing from W0 prime. Then we can see that these 2 geodesic rays are asymptotic in the universal covering if and only if the following condition holds. We have a sequence of black regions such that each BI is adjacent to both WI and WI prime. Okay? And moreover, if I is even, WI plus 1 is obtained from WI by counterclockwise shift. And if I is odd, this is counterclockwise and this is clockwise shift. Okay, let me show you one example. This is a Brownian ring. This is a key proposition. Okay, we consider Brownian ring and consider 2 white regions, W0 and W prime, and consider a geodesic ray starting from here. Okay, and we like to construct a asymptotic pair of geodesic rays. Then now W0 and W0 prime, for these guys, we have a pair, we have precisely 2 black regions which are adjacent to both W0 and W0 prime. So for example, just choose B0 to be this one. Then W1 is obtained from W0 by shifting in this way, and W1 dash this way. Okay. Now let's look at this guy. Then we have 2 black regions, but this black region is already used, so we must use this black region. Then we do this way and obtain this picture, and repeat. Then there's a unique way for this way, and we come back to the original position. And if we choose another direction, then it goes just move backwards. So if you choose this one, then you go this way, but you choose another one, then just go the other way. Okay? And another example is here. Okay, so from this fact, we can see the following. For Whitehead ring, we consider these regions and consider corresponding subgroup. Then the intersection of this subgroup is equal to the infinite cyclic group generated by this longitude. And so the intersection of this limit set is equal to the limit set of this single element. So it's a single point. But for this particular example, we have a simple proof because as we learned from last lecture by Andre Dessny, the Borromean ring is a right angle ring. So we can see that this surface is actually totally geodesic, and this is a round circle. From this, we can see this one. Okay, and for torus ring, we have some strange phenomena. Even if they don't share common vertex, we obtain this cycle. But this phenomena occurs only for two-bridge rings. Okay. And finally, I'd like to explain this example. Okay. So for Higayako note, we start from, we consider these white regions. Okay, so in this case, W0 is here, and W was here. So every black region, B1, B2, B3, shares an edge with W0 and W4. So we have three choices from the beginning. So this makes the situation very complicated. And so I don't have time to explain this, but by some analysis, we obtain this picture, and we can understand all asymptotic ways from this picture. And finally, we can see that the intersection of these subgroups is generated by these elements. So it's a rank 3 group, and we have this generating system. And I think, or I hope, we can do this task for every alternating link. Okay, that is all my talk. Thank you very much for your attention.
Yes.